So thank you guys for coming. I'll go ahead and get started here. So first thing we're going to cover is what is Monad from a developer perspective and what is Monad from a user perspective. So what is Monad? You probably heard about it online in some form as parallel EVM. It's a lot of other things than that, so we're going to go through those today. Really what it is a from scratch redesign. It looks very similar to Ethereum in shape. That means you have full EVM L1 equivalent blockchain. If you've done any developing on an EVM before, it basically feels the same to you. But you get to tap into a high performance system, 10,000 transactions per second. When we say 10,000 transactions, we're not saying transfers per second. We mean real historical Ethereum transactions. We actually run Ethereum state through the blockchain. So when we're saying 10,000, we mean 10,000 real transactions. We're also able to give developers single second block times and single slot finality. And we maintain full EVM RPC compatibility, so anything you're used to working with as far as like wallets, indexers, that type of stuff kind of just works out of the box on EVM. So from the human perspective, really what it is it's a place where Ethereum apps can kind of find a home and kind of realize that vision of the world computer. It's high performance, low cost system, hundredths of a cent for Uniswap v2 transaction, and we're trying to stay true to decentralization, so that means hundreds of nodes participating in consensus around the globe, while maintaining reasonable hardware requirements. And we'll go through how that's possible here in a second. From a developer perspective, it's a fully EVM equivalent L1. You can basically just port over any contract, tap into existing EVM research and network effects, and as I mentioned before, high performance and full RPC compatibility. Now, we're kind of going to walk through like how all this is possible, and so we really need to look at the bottlenecks of normal distributed systems and kind of what exists before and how Monad addresses these bottlenecks going forward. So there's really 4 fundamental constraints in a blockchain. It's network bandwidth, which is essentially like your internet overhead, CPU throughput, how fast your actual cores on your computer can run, state access, so this is like the database and the historical state of the chain, as well as state growth, which is like current accounts and their balances and things like that, and the ability to pull those up. So kind of what's existed before is like we see a lot of blockchains doing things to get certain properties by taking some shortcuts. And one of the easiest shortcuts to do is essentially just make you have a really good internet connection. So we are about 100 megabits per second internet is what we're targeting for a consumer full node. A lot of blockchains run on 1 gigabit or 10 gigabit connections. Obviously, if you up the bandwidth requirements, you can just scale that way. Obviously, it costs more money to have a better internet connection. Another way people can achieve some of these properties is just by putting all the nodes close together. You can't cheat physics. Like the speed of light takes time to travel around the globe. So how do you cheat physics? Well, you just put all the nodes in the same place, and then the speed of light's a lot shorter because the distance is a lot shorter. And then another thing we see a lot of people do is just like upping the RAM requirements. Obviously, this makes nodes very expensive. RAM is the most expensive piece of any computer system. And so having that really low latency memory is actually very expensive. If you're asking people to store the entire state of a blockchain in RAM, you're looking at a very expensive commuter. So yeah. So really, what are our goals? We really just want to get the most out of commodity hardware. We need to design software that saturates the hardware through all these subsequent bottlenecks while preserving decentralization. And that means reasonable RAM requirements, fully globally distributed, hundreds of nodes. And how do we do this? Well, it's really through a new software architecture that looks at all these things and finds the best way to saturate each bandwidth through these different bottlenecks. So it's actually a full new redesign of the architecture. The only thing we really kept is the EVM bytecode. So that means the instructions of how the EVM interprets code. But we rebuilt, fully rebuilt consensus, fully rebuilt our execution engine. We implemented parallel execution, and we also have a fully custom state database called MonadDB. Today we're going to go through The later 3 of these, consensus takes a little more time. I don't think we have time for it today. If you have any questions about this, feel free to come ask me after. I'm happy to answer some questions on it or send you some docs to read more. So the first one we're going to look at today is asynchronous execution. And in order to do that, we kind of have to look at how most blockchains work today. And this is through something called interleaved execution. So this is really the opposite of asynchronous execution. So what is interleaved execution? It basically means execution and consensus are done in tandem within a block time. So for Ethereum, it has a 12-second block time. This is kind of like how long each block has to come to consensus on it before a new block is proposed. And we see execution in Ethereum is like 1% of the block time, and consensus takes way more time. Why does it take way more time? Well, because it's nodes talking around the globe, obviously speed of light, it just takes a lot of time. So in typical blockchains, we get something called interleaved execution. We see execution up there in the dark blue, consensus in the light blue, and the blocks surrounding it is the block time. So obviously as blocks are produced, it basically just goes in a chain, and we get something that looks like that over time. If asynchronous execution, it really stems from the realization that you can pull execution outside of consensus, or outside of, well, basically it stems from the fact that if you have a deterministic state machine, such as the EVM, you know the ordering of the transactions and you know the data in each transaction, you actually don't need to execute to know that the results are always going to be the same, right? Because if you have, like x plus y, equals x plus y, right? And you know x and you know y, you know how to do addition, right? It's always going to answer that, right? So as long as you specify what x and y are, you're going to know the output. So realizing that, what we knew is we can actually pull execution out of the current block and do it in tandem with the next block. And so you can actually do ordering in parallel with executing the previous block. So you're ordering the current block while executing the previous block. And what that allows us to do is something like this, graphed. And the one thing you want to notice here is now consensus and execution are on different sides, right? And so we're actually coming to consensus on what the data is, what the order of the data is, and then we will execute it after we know those things in tandem with coming to the ordering on the next block. And so if we look at them side by side, it looks kind of like that. Go ahead and put some block time things there, and you see how some of them overlap. And what that allows us to do is to then do the magic. Now that we're doing two things in parallel, the execution can take up the entire block time. We're not actually constrained to doing them in the block time. And so we are executing the previous block while coming to consensus on the ordering and the data in the current block. And so what this allows us to do is basically greatly expand the execution budget, which allows us to basically expand the gas budget, which translates to obviously higher throughput, lower fees, and all the properties we went through at the beginning. Yes. So yeah, I kind of explained a lot of this ahead of time, but just to review, basically nodes come to consensus on the transaction ordering prior to execution. We're working on two blocks in parallel. There are some caveats around how we have to do checks to make sure that all the nodes are in sync. Basically, nodes have a delayed view of the state. And so after they come to consensus, they have to execute locally to get that state, and then that goes through consensus at a later point to make sure that all the nodes are agreeing to the same state changes. But yeah, it allows us to greatly expand the gas budget. We see a lot of blockchains moving this way. There's actually current proposals in Solana to do the same thing. It's kind of one of those engineering things that once you realize it's possible, it's well, there's not really a lot of downsides to doing it, and it gives you a way bigger gas budget. And so, yeah. The one thing to note here is that finality is at consensus time. even though we are executing the blocks later, like I said, if you know the order of the data and you know the data in each block, it's actually final at that point because you know the way that the EVM works, right? And so if you have a full node, you can just run those transactions locally as soon as you come to consensus and basically get immediate update of the state as soon as consensus is finished. Okay, that was asynchronous execution. Next one we're going to do here is parallel execution. This is probably what you've heard of Monad about. A couple months ago, it kind of became like the hot topic within Twitter. Everyone was talking about parallel execution. So we're going to go through how Monad does this. Very simple view of what parallel execution is taking one lane and turning it into multiple lanes. Computers today have multiple cores. It's kind of ridiculous if we're not using them. So let's go ahead and use the hardware. So today, transactions are mostly linearly ordered and serially executed. This is kind of the logical thing that you think about in your head, right? Transactions come into the block, they have an ordering, and then they're just executed in that order. What we really want to do is maintain this ordering that consensus gives us, but execute everything in parallel and get those results much quicker, and then commit them in the order that they came in. And so how do we do that? We do this thing called optimistic parallel execution. Has a couple different names, software transactional memory, OCC, optimistic concurrency control. But really what it is kind of the most obvious thing. So you basically start with a synced view of the world. You assume everything can be run in parallel. You go ahead and generate a bunch of pending results. You then walk through the pending results in order, trying to commit them. And if you see that there's any pending results that relied on a previous one, you then re-execute them. And so how does this work? We're going to do a really simple example here. We have me with 1,000 USDC, Alice with nothing, Bob with 300. I want to transfer 100 USDC to both of these accounts. Obviously, what we do expect it to come out to is me having 100, me having 800, Alice having 100, and Bob having 400. We can have some transactions in between there that are unrelated, and you'll see how this affects the execution as we go on. So basically, to start, we just assume everything can be executed in parallel. And so we just generate some pending results. Then we start stepping through them and we say, okay, cool. I had 1,000, 900. We commit this. We don't see any conflicts. The starting state is what we assumed it would be. Move on to the next transaction. Oh, it doesn't affect any of that stuff. Move on to the third transaction. I just committed that I had 900, and this is saying I had 1,000, right? So there's a conflict here. And so how do we resolve this conflict? Well, we just re-execute it with the new state, and bada bing. So one thing to note, we basically run a bunch of transactions assuming the same starting point. We produce a bunch of pending results, commit those, and re-execute if necessary. Now, the way the algorithm works is that because we're committing them serially, you never have to actually execute a transaction more than once. And if we think about what actually takes the most time in a computer, it's actually calling up the state for that transaction from the database. Execution is incredibly cheap. The thing that actually takes a lot of time is going to the hard disk, reading out a hard disk, rolling it into RAM, and then execution from there is actually very light. And so what that allows us to do is basically the overhead of re-execution is actually not that high because we've already cached all the state ahead of time. So even when we do have to re-execute, it's a pretty light thing. Now, one cool thing about this model is you don't have to deal with access lists. Access lists obviously are a little bit hard as a developer to deal with. They also take up bandwidth. So when you have to send in more information to the blockchain, obviously that takes up more overhead on bandwidth. And so essentially you get this familiar interface that you're used to working with an EVM while still maintaining the performance on the back end of a parallel system. So that was parallel execution. But what really makes that actually possible is MonadDB. And so we're kind of going to walk through the magic here of what MonadDB is. Bear with me, this is probably the most complicated part here. But yeah, let's dive in. So what is MonadDB? It essentially makes Ethereum state native to how Ethereum works logically. And so what does that mean? Well, it is the thing that feeds the parallel execution and keeps it saturated by allowing you to have parallel state access. So you basically, like I was saying before, you need to pull up the dependencies from the database. If the computer is sitting there waiting to do that every time like a transaction is trying to be executed, it doesn't actually matter if you have parallel execution because you'll just be waiting on the database for every transaction to pull everything out. And so really what you need is you need asynchronous I/O so that you can just issue a bunch of requests to the database in parallel, and then as those come back, immediately execute. Yeah. So some background on modern day hard drives. They're actually like pretty cool pieces of technology. For about $200, you can get a very high bandwidth SSD with about 1 million I/O operations per second. Yes, it takes about 40 to 100 milliseconds to do a lookup versus RAM, which is about 0.1 seconds, but you can do a lot more at once. And so basically, it's just really important that we saturate this memory bandwidth and always be pulling things out of state in parallel so that the other parts of the system are not bottlenecked waiting for things to happen. So the other piece here is kind of how Ethereum, and this is probably the most complicated part here, is how Ethereum actually stores state. It stores state in something called a Merkle-Patricia trie. A lot of people call it a Merkle-Patricia tree because it's a tree structure. The technical term is a trie. A lot of other databases like Go, Ethereum, and Level, and Aragon, and these other clients, they essentially use an off-the-shelf database in the back end to store this tree. Now, those databases themselves are not a Merkle-Patricia trie. They're usually like a B tree or like an LSM tree, just like other tree structures that normal databases use, because in other domains of computer science, like those are efficient lookup storage. Now, why do we want an MPT? Because this is almost like the main philosophical reason Ethereum exists. It allows you to do succinct verification of transactions and state. And what that means is you're able to check the root of something and tell if all the data under that root is as you expected. So, and a lot of other blockchains that don't have a Merkle-Patricia trie, what you actually have to do to see if a transaction is included is download the entire block, re-execute one by one, and then figure out if it's there, right? With Ethereum, they believe that it's very important to be able to just look at a block and verify that the transaction actually happened. And the data structure they use to do this is called a Merkle-Patricia trie. You can imagine it as a bunch of data in leaves at the bottom, and then subsequent pairwise hashes that go up this tree such that if any one of these data elements have changed, the hashes subsequently going up to it would have changed. And so if you have this root hash, you basically know that everything in the bottom is as you committed to it. And if any of those were to be like lied or changed, like it would have to generate a different hash. Now, you can do that without a Merkle-Patricia tree, but like I said, the overhead is then downloading the entire block, getting the historical state, executing one by one, making sure nothing messed up. And so really this is why Ethereum is Ethereum, right? Like it wants to provide succinct verifications for things that have happened on a blockchain. And so this data structure, there are no databases that actually are built like that. Because in most domains, that's not like the efficient way to store data, right? Because they're not doing what Ethereum is doing, which is providing succinct verifiability. That's kind of one of the main value props of Ethereum. And so what that means is they have this logical idea of a Merkle tree, but they have a physical tree that's not a Merkle tree. And so logically, when they're transversing from one node to another, they're going into this backend data structure that doesn't look like a Merkle tree and doing a bunch of other lookups for it. And so what that turns into is a tree traversal within a tree traversal. Because as you're basically going from the root hash to the next hash, you're saying, okay, what's your child? And that what's your child means going into LevelDB or PebbleDB and traversing an LSM tree to find it, which is anywhere from like 16 to 32 times more overhead. So what does MonadDB do? It's a full rebuild of a database where the Merkle-Patricia trie is the actual way that we store data on disk. And so we basically remove this entire tree indirection. And when you go looking for this data in the Merkle trie, it's actually how the database itself stores it. So even if you were to store text or numbers in MonadDB, it would actually be in a Merkle-Patricia trie. And so for Ethereum, obviously this is a great match. And what that allows us to do is basically, like I said, 16 to 32 times less lookups per traversal of the tree. Combined with this concept I was talking about before, asynchronous I/O, where you can pull up things in parallel as you're executing things, it basically allows us to saturate this parallel execution thing that you've probably heard a lot about, and keep the compute saturated by having state access be very, very efficient. So, I think I went through a lot of this in pretty verbose talk before. But essentially, all these things allow us to have a custom state database where the Merkle-Patricia tree is natively structured on disk. We use this kernel technology called IOU ring that allows us to do asynchronous I/O. And this allows us to spawn a bunch of parallel threads or parallel lookups at the same time and have those fed back into the parallel execution engine. And this basically means we have parallel state access as well as parallel execution. And that really is the secret sauce that makes parallel execution actually work. Yes. So that was MonadDB. Hopefully you guys followed along. It's a pretty complicated explanation with no images. So hopefully I did a decent job there and I don't lose my job as a DevRel. Yeah, so thank you guys. If you want to reach out, you can go ahead and reach out to the Monad account. You can reach out to me either on Twitter or on Telegram. That's my Telegram as well. Yeah, happy to chat about any of this if you have any questions. But thanks for listening.